Hey, welcome back, guys. So yesterday, or last class, we talked about how to write one of these expressions. Okay? And we said this came about knowing the fact that when our forward reaction speed is equal to the reverse reaction speed in what we call a reaction equilibrium. We saw how when coefficient is changed, Kc will change. Knowing how when things go in the reverse, you take the reciprocal. When a reaction is a stepwise reaction, you multiply the two equilibrium constant. That's good and all. That's what I was gonna say. But the most important part is being able, if you know what K is, if you can find out using those handbook what K is, are you going to be able to predict at equilibrium what is the concentrations of your entities? Now, before we get there, we're going to look at equilibrium constant in more of a detail in the extent of how the reaction work. Now, if you were to calculate K, okay, at a certain temperature, at a certain pressure, not standard-wise, if this K value is greater than 1, what you'll know is that the reaction is mostly products. That this reaction, okay, is a lot of products more than reactants. It's product dominated, we would say. If K value is less than 1, so it's 0 point something, obviously the numerator is smaller than the denominator. And we know that for a reaction, okay, the denominator is the reactant. The numerator is the product. So if this number is smaller than that number, that means this reaction doesn't drive that much product. This reaction is still a lot of reactants. So it's crazy to see some of these K value in our CRC handbook. That some reaction just dominates being a product. Some reaction dominates as a reactant. It still form products. Oh yeah, it still form products. But when the rate equals, there's more products than there is reactants. We'll see some of these things later, and most likely we're going to be looking more into calculating at equilibrium what these concentrations are. Oh, we're going to be doing some serious math here today, some really serious math. So let's take a look at problem number 1, because I have so many for you. So in this question, it says, determine if reactants or product was dominant in this reaction. Determine if reactants or product was dominant in this reaction. Okay, I have this reaction. Okay, and here's my K value. Is this reaction going to be reactant dominant or is it going to be product dominant? Because Kc in this case is a number greater than 1. Okay, so let's take a look. If you have, let's do the Kc expression. The Kc expression here is this. You don't really need to do this. I mean, it's pretty obvious what the answer is going to be. Okay, it's 46. 46 means, oh, the numerator must be bigger than the denominator to get 46. If not, you'll be getting 0 point something, right? So since the numerator is bigger, that means this reaction drives products. It's more product dominated. Because Kc is greater than 1. Okay, so product will dominate. Okay? Will dominate. More like will dominate. There you go. It's a very simple question. Just to see if you understand the theory. Here's some more serious question. Oh my goodness. Let's take a look. Determine the equilibrium constant. Okay. I'm finding K between hydrogen reacting with iodine to get hydrogen iodide. And I even balanced it for you. The ratio is 1 to 1 to 2. Make sure you balance it right, or else your Kc expression is going to be wrong. Now, this is the tricky part, though. This is the tricky part. Earlier, last class, I gave you something very similar to do to calculate for Kc. So let's go back to last class and look at what's similar about this. It was something like this. Same equation. Okay? Same equation. But what did I give you here? I gave you, you have to read carefully. How you get it? Read carefully. You don't get it. But yeah, it says at equilibrium, the equilibrium concentration, meaning that when the forward reaction already equal the rate of the backward reaction. The forward reaction this way is as fast as the backward reaction, which we now have an equilibrium. The concentration for these guys are these respectively at equilibrium. Take a look at this question. You started. Oh my God. You started. So that means these numbers that I'm giving you right here with the volume, which you can get molarity from, is not at equilibrium yet. You just started. You just started. It's not at equilibrium. You want to know, what is it at equilibrium? Well, I did give you one value though. It says after equilibrium or at equilibrium, HI, which is this, is 1.6. Let's write the expression first. We know that it's going to be HI squared divided by H2 times I2. Okay? That's for sure. Kc is equal to 1.86 squared divided by, what is this going to be? What is this going to be? Because I didn't say at equilibrium what H is. I didn't say at equilibrium what I is. I just said in the beginning, H2 is 1 mole over 1 liter. So that means initially, hydrogen was 1 molar. I2 initially was 2 moles over 1 liter. So that's 2 molar. Initially, not after during equilibrium. This is a bigger problem. It's a huge problem. If this is what we got initially, then what is equilibrium? All right. To do this kind of question, you need to set it up correctly. And to set it up, you need something called an ICE table. ICE. I-C-E. I stands for initial. C stands for change. E stands for equilibrium. Hence ICE. So initially, let's do this, and let's do this carefully. So initially, you have two reactants in a reaction vessel. You're going to put in 1 molar worth of H2 and 2 molar worth of I2. Now. What would be HI initially? I hope you say 0. I hope you say 0. Because initially, it's almost like you didn't even mix these guys yet. Oh my gosh. You didn't even mix these guys yet. You didn't do nothing yet. You have this in a bottle. You have this in a bottle. They didn't mix, so why would you have this? So this initially started as 0. However, things gonna change. Okay? Things gonna change. And it's changed by molar coefficient. The molar coefficient here is 1, 1, and 2. So you can pretty much bet that every time this reaction proceed, you're losing 1 mole, you're losing 1 mole, and you're gaining 2 mole. So, change is based on your coefficient. Why do you think we spent so much time balancing equations back in the days? You think it's all for nothing? Man, you know it's for everything. In terms of change, it's going to be minus 1x because we don't know how much it changed really. We don't know how much it changed. We know it's 1 mole of something. Same in here. Negative 1x. We don't know how much it changed. We know it's 1 mole of something. Here it's going to be plus 2x. We don't know how much it changed, but we know it's 2 mole of something. So that's something we are calling x is what we want to find. If we are able to find x, we are home free. So, let's continue. We know initially that it is 1, 2, and 0 in terms of change, negative of x for H2, negative of x of I2, and plus 2x for HI. Because when things change, when the reaction proceeds, every time it proceeds, you lose 1 mole of this, 1 mole of this, and gain 2 moles of that. But we don't know for sure how many of that 1 mole of what. So at equilibrium, you're just writing this out. It's going to be 1 molar minus 1x. So in this case, 1 minus x. Okay, you're just putting this together. For I2, it'll be 2 molar minus 1x. For HI, it'll be 0 molar plus 2x. It's ugly to write it this way. It's really 1 minus x, 2 minus x, and 2x. That's what it really is. Okay? Again, our ultimate goal here is to find what x is. Can we find what x is? Now think about what you already have here. Think about what you already have here. This is a big clue right here to find x. It says that at equilibrium, when equilibrium has established, you mean here? Here? So when equilibrium has established here, HI is 1.86. That means 2x, whatever that is equal to 1.86. Whatever this is at equilibrium is 1.86. I know my algebra. I know what 1.86 divided by 2. That's 0.93. There you go. I found X. I found X. All I have to do right now is plug this X back into my other entity. So for hydrogen gas, 1 minus X, which is 1 minus 0.93, okay, is equal to 0.07. I2, 2 minus 0.93 is 1.07. This is beautiful. Because right now, I can go back and finish my question, which I already started, but I had trouble getting these guys. But now I have these guys because I know at equilibrium what they're going to be. And it makes perfect sense if you think about it. This reaction started like this, where you're not at equilibrium, that's for sure. You had nothing here. So the reaction didn't even proceed yet. Once it starts proceeding, you're going to get less and less of this. You're going to get less and less of this. You're going to get more and more of these. And how much less? 1x less. How much less? 1x less. How much more? 2x more. Well, at equilibrium, yes, you went from 1 to 0.207. You went from 2 to 1.07. You went from nothing to 0.93. This right now is the concentration at equilibrium based on what this question is telling me. So what is the equilibrium constant? Kc is equal to 1.86 squared divided by 0.07 times 1.07. Kc ultimately 46. That's the equilibrium constant. So for this reaction, it is more product driven, meaning that at the very end, you're going to get more products, which is not surprising here, right? Look at this, such a much bigger number than these guys. Hopefully you got it. Okay, this question is a very good starter question. The reason why it's a good starter question is because it allows you to understand exactly what equilibrium is and what is going on if you're totally lost with this aspect of concept. Let's do the next question. This is an interesting question. Can be hard unless you use your head and you really know your math. Now, some of you I know is very good at math. I know. Mr. Lazeski tells me that you guys are awesome in math. All right, so H2 is equal to I2 and is 24 molar. We're mixed and heated to 490 degrees in a container. So it seems like this sentence is saying that the concentration of H2 and I2 is 24 molar, and that's kind of like in the beginning, meaning that that's going to be an initial statement. Calculate the concentration of all the entity at equilibrium, given the fact that Kc is 46. Oh no. This time, I want to know what this is, and what this is if Kc is 46. If 24 molar is the initial. Now, this is not hard, okay? This is just really working backwards, but really not doing things backward. Working backwards is different than doing things backward. You're trying to find something given that you were given answers to the last time. So let's take a look at how to do this. Again, it's very mathematically sound. So you started off with 24 molar of H2, 24 molar of I2. How many molar of HI did you have? Just like last time, it didn't say, so it must be 0. You had nothing to begin with. Again, the change. Well, when this reaction proceeds, you're going to be losing 1 mole all the time. Again, I2, you're going to lose 1 mole of something all the time. For HI, you're going to be gaining 2 mole at a time. 2 mole of something at a time. Remember, that's something. That's something. It's always something. I want to know what is E. Let's get rid of these question marks for now, because we don't know what E is. We're going to find out what E is, but we know the expression to find E. The expression to find E for H2 is 24 molar minus X. The expression to find I is also 24 molar minus X. The expression to find HI is 0 plus 2X. What is X? Again, we're looking for X. Man, X is really annoying me. Oh, unlike last question, which I did give you, last question I actually gave you what HI is, so you can find X by doing substitution or just solving it for the equation. But this time I didn't give you any equilibrium concentration. So I never said here at equilibrium. I never said at equilibrium that one of these is a certain number. Because if I did, you would have make that equal to that number. No, I didn't give you anything. I did give you KC. Oh my gosh. If you're thinking math, you should think to yourself, okay, this is not good. This is not good. Let's take a look at the KC expression. The KC expression, which I wrote probably 100 times now, is HI squared over H2 times I2. Let's plug everything that we know in, okay? Let's plug everything that we know in. KC is 46. Ooh, whoopee-doo. Okay, HI is 2x, right? 2x. You can plug that in there. Square. Oh, be careful here, eh? A lot of students do this, 2x squared. No. That's not the same thing as this. You should know that. Okay? If anything, this is actually 4x squared. Divided by H2 is 24 minus X. I2 is 24 minus X. Now find X. And you're probably saying, oh my gosh, this is going to be messy. So messy. Oh man, I see quadratic. And every time I see quadratic, I get a headache. Well, you know what? In some cases, you are going to do quadratic. You are. Just can't avoid it. But can you manipulate this equation in a way that you can avoid quadratics? That's the question. Let me show you some mathematical strategy. Not no math teacher. Lazeski is. Isn't this the same thing as saying this? Right? And isn't this the same thing as saying this? Right? Can you bring this over here and just root this and you totally get rid of that square? Because that is a square that creates quadratic situation. Yeah, you can. You can root this. That way you get rid of this. Now you'll never have a situation where you have a quadratic, because quadratic sucks. You have to use the quadratic formula to solve, and that creates problem. At the same time, it gives you two answers. Well, let me just let you know. There are going to be times we're going to have to use the quadratic equation. And if it does give you two answers, always eliminate the negative one. Only keep the positive one. We don't like negativity here in chemistry. We only like positivity. So if you do that, you'll notice that X is equal to 18.56. Yes, I already did the math for you. Okay? But I want you to actually do the math and get that. For practice sake, man. It's not like I'm asking you to find the derivative of some sort of trigonometrical thingy. Even though if I guys should do that, it's not going to be that hard, right? I better shut up. All right, so let's finish this question. I think I can finish this question now. So at equilibrium, okay, I know what H2 is, I know what I2 is, and I know what HI is. H2 is just 24 minus X, which is 24 minus 18.56, which is 5.44. I2 is the same thing, 24 minus 18.56, which is also 5.44. HI is going to be 2 times 18.56, which is 37.12. Okay? Makes sense. And if you want to check your work, all you have to do is put these numbers back into your expression. And you should get 46. All right? Again, either you see it or you don't. You know, the chemistry part is not that hard, but sometimes it's the mathematical part that can be tricky, and those silly mistakes kind of just creeps up on you all the time. Now, here's another question. Okay? I'm not going to do this one. I want you guys to do this one. The thing is this, though. I'm going to let you know right now. I'm going to give you some bad news. For this question, you have to use the quadratic equation. I'm sorry, but this one you cannot avoid it. Okay, you're going to have to use it to find x, to be able to find your equilibrium concentration. But I'm going to start it for you. Okay, I'm going to even balance it for you because I'm a nice guy. I'm even going to set the ice table where this is going to be 0.5. This is going to be 0. This is going to be negative an x. This is going to be positive of 2x. Equilibrium-wise, it's going to be 0.5 minus x. This is going to be 2x, or 0 plus 2x. Really is 2x. Set this up to find Kc, which I give you to be 4.5. Use the quadratic formula to find out exactly what x is and sub it back in here. All right. Yeah, we'll take it up. I was going to say I'm going to give you the answer, but you know what? I'm not going to give you the answer. I'm going to see if you guys can get the answer, and we'll find out what the answer, and then I'll let you know what the answer is tomorrow. Okay? So do that, please. Here's another question. Okay? In this question, I'm going to show you something. Theoretically, you have to use the quadratic formula. But I'm going to show you how you can avoid it. Because for this question, it is avoidable. And it's not some mathematical trick like we saw with the other problem. No. It's called the 100 rule. So here's the reaction. And here's the ice table. Okay? We started with 1.5 molar of this. And obviously, initially, you have none of these and none of these. The good thing is, this reaction don't need to be balanced. So therefore, you're losing 1 mole of something. You're gaining 1 mole of something. You're gaining 1 mole of something. So the equilibrium expression is going to be 1.5 minus x. Here is going to be x. And here's going to be x. Or let's make it 0 plus x. Some people like to see that for some reason. I don't know why. Okay. Okay. Let's do the Kc expression. Kc is equal to cobalt times chlorine over cobalt 2 chloride. Okay? let's sub in those numbers. 2.2 times 10 to the power of negative 8 is equal to x times x over 1.5 minus x. I don't know why I put a bracket here for no reason. Okay? Find x. I'm not going to do quadratic formula. I'm not. Because I can sense the fact that x is a very, very, very small number. So small that when you take 1.5 minus x, it's not going to make a difference at all. You're still going to get somewhere near 1.5. And I'm going to test that. And to test that, we use something called the 100 rule. 100 rule means if this number is greater than 100, if it's greater than 100, 1.5 minus x, just make it 1.5. Now, if this is less than 100, too bad. Do your quadratic equation. Suck to be you. So let's test it out. Let's test it out. Now, to do it is very simple. You take 1.5, which is the original concentration, okay? And you're going to divide that by Kc. So you take the original concentration and you divide it by Kc. You can do it for everything. If there's two reactants, you can do it for both. Just to eliminate this situation. You don't want this situation. This situation is what makes it suck. All right. This is 1.5 divided by 2.2 times 10 to the power of negative 8. I can tell you right now that this is going to be a huge number. This is the amount of money I have in my bank account. Is this bigger than 100? Hell yeah, it's bigger than 100. So that means this is true. Why is that a good thing? Take a look at this. Take a look at this. Look how clean this looks now. Look how clean this looks. All you have to do is multiply this by 1.5. This is gone. And you take this over here and root it. You totally avoid a quadratic. X, x2. X in this case is a very small number. Looking at 0.000182. Okay? So if you were to take 1.5 and minus this number, it's really still 1.5. And that's exactly what we're going to do. Okay? So to answer this question, ClCl2 is equal to 1.5 minus 1.82 times 10 to the power of negative 4. And the answer is 1.4998. So it didn't go down much. It's not supposed to. Look how small Kc is. Kc is a really tiny number, you know. So tiny that is totally in the beginning of today's lesson, reactant dominant. You're not going to get much of these. Because none of these, this hasn't gone down much. Look, it didn't go down much. But there's still something, I guess. There's still something. There's really some cobalt, and that's just X, which is equal to 1.8 times 10 to the power of negative 4 molar. There is some chlorine, not much, same thing, 1.82 times 10 to the power of negative 4 molar. Okay? Very easy to do. But the understanding, of course, is what I really, really want you to do. Now, you may be thinking, how come you didn't tell me a 100 rule here? Well, why don't you do 100 rule and see if it works? There's your Kc. Take this and divide it by this and see if you get over 100. If it does, you get to scrap this. If not, too damn bad. You have to use this. I can tell you right now, is the latter. Ha! All right. I have one more question here. Okay. Again, it's also another question that I want you to do. So I want you, no, I'm not going to help you guys out to begin with. I want you to read this and I want you to solve this, and we will take this one up together the next day. So I'll take two questions up. I'll take this one up and I'll take this one up, which is already kind of half done. And yeah. Oh, I'll give you a clue. I'll give you a clue. You maybe want to think, do I have to do quadratic for this? The answer is no. But it's not a obvious no. And if you want to, go ahead. I just want to know the answer. All right. Bye, guys. Have fun.